IEEE Computational Intelligence Society webinar toward fair and reliable performance evaluation in evolutionary multi-objective optimization. We're delighted to have you with us. I'd like to begin by thanking Ying, Chair of the CIS Webinar Committee, for her leadership in organizing this session, and express our appreciation to our speaker Lee for sharing their expertise with the community today. Before we get started, we have a few housekeeping notes. One, lines will be muted throughout the presentation to ensure clear audio. You may enter questions in the chat box at any time, and we will reserve time at the end of the session for Q&A. The webinar will be recorded and posted online after the webinar is over on the CIS website at cis.ieee.org. We invite you to stay connected with the Society and learn about future events by following us on Facebook, LinkedIn, and Twitter. I'll be putting those links in the chat as well during the session. Thank you again for being here. We look forward to an engaging and insightful session, and I will now turn it over to Ying.
Hello, everyone. It's my honor to introduce Dr. Meng to give a webinar today. Firstly, I would like to introduce Dr. Meng. She received her Bachelor of Engineering degree in Electronic and Telecommunication Engineering and a PhD degree in Electronic Engineering from the Faculty of Engineering, University Malaysia, Sarawak, Malaysia in 2012 and 2018, respectively. She is currently a research associate with the Department of Computer Science and Engineering, Southern University of Science and Technology, China. Her current research interests include evolutionary multi-objective optimization and fuzzy systems. She is an IEEE senior member and a member of the IEEE Computational Intelligence Society Evolutionary Computation Technical Committee. She received the Best Paper Award at the IEEE. So please join me to welcome Dr. Meng.
Yeah, so thank you very much for the introductions. Okay. So I should start now. Okay, so thank you very much, and thank you everyone for joining this webinar. So today my talk is on this toward fair and reliable performance evaluations in evolutionary multi-objective optimizations. So before I talk about the performance evaluations in evolutionary multi-objective optimizations, okay, I would like to first introduce what multi-objective optimization is. So this is a very brief introduction. So basically, almost all problems in the real-world applications have multiple objectives. So our goal here is to find a set of trade-off solutions that can approximate the best trade-off solutions. And these best trade-off solutions, we usually call it as a Pareto front. And because this is because the problems here, they are usually conflicting with each others. So we usually cannot get a single solutions that optimize all the objectives simultaneously. And so this is the reasons why we have trade-off solutions. And if we look at this figure here, so this shows the number of papers with multi-objective optimizations in the paper title based on the Scopus database. And we can see that there's an increasing trend, increasing attention over the last 10 years in this topic. And for evolutionary multi-objective optimizations, the general goal is to find a good approximations of the Pareto front. So by good approximation of the Pareto front, we mean we want to have a set of solutions which is converged to the Pareto front and well distributed along the Pareto front. And this approximated Pareto front is then shown to the decision maker as a result of a single run of an EMO algorithm. And the decision makers can select a best solutions based on this Pareto, based on the solutions on this Pareto front, based on their own preferences. And so for performance comparisons of EMO algorithms, basically it's the comparisons of solution sets. In single objective optimization problems, it's very clear that which solution is better. So because we need to, we only minimize one objective So it's easy to compare two solutions based on a single objective function values. From this figure here, we can easily tell this pink solution has is better than these green solutions because it has smaller objective values. But for multi-objective problems, we have solution sets. So for the solution sets obtained by two different algorithms, it's not so easy to say which solution set is better. So if we focus on the convergence, we may be able to say that this is a better solution set than the green solution set. But if we also want the diversity of the solutions, then maybe we want to say this green solution set is a better solution set than this pink colors one. Now, to give you a more better understanding on these situations, here we have 4 different solution sets. So all the solutions are on the Pareto front. So here we do not have to worry about the convergence of the solution set. We only need to focus on the distribution of the solution set. So for these 4 solution sets, which is the best solution set, we may want to ask. So each of these solution sets have different distributions. And by visual inspections on these solution sets, we would agree that solution set 1 is a better solution set, or we think that solution set 1 is the best solution set. This is because this solution set, the solutions are well distributed over the entire Pareto front, and we would not say this solution set 4 is the best because it only has the boundary solutions. And for the 3 objective test, may be easier to visualize because it's on a three-dimensional plot. But for the many objective problems, for example, if we have a 4 objective problem here, it's not easy to tell which solution set A, B, C here, which is the best solution set. So usually for many objective problems, we use the parallel coordinate plot to show the solution sets. And here for each axis here, vertical axis here, represent the values of different objective functions. And a solution is represented by this connecting line. So this line is one solution. So for this 3 solution set, it's clear that this solution set A is not the best because here we can see that it do not cover the entire range of the Pareto front. So, but for B and C, it's not easy to tell which one is better. And the C looks more regular, so we may want to say that C is a better solution set than B. Then to see it more clearly, here we project the solution set of the 4 objective problems onto a 3D plot, and also we use additional we use the colors to show the values of the 4th objective functions. And from here we can see, based on these visualizations, solution set B is the best solution set because it has solutions in both interior side and also the boundary of the Pareto front. Whereas this solution set look very regular and uniform in this parallel coordinate plot, it actually contains only the boundary solutions. So here we show that the visualizations for many objective problems is difficult actually. And here is a slide to explain why we want to do the performance comparisons of EMO algorithms. The goal of performance comparison, actually this is not only applicable for EMO algorithms, it's also applicable to any algorithms. So the goal actually is to identify high-performing algorithms, and we want to understand the strengths and weaknesses of the algorithms on certain kind of problems. And based on those understanding, we can support the algorithm selections in real world, and also we can guide the algorithm improvement for the field. And by performance comparisons, we usually have we will have a ranking of the algorithms, which is the best, which is the second best or third best. So a ranking is only meaningful when the comparison is fair. Otherwise, the winner may be the results of biased experiment setting. And in this talk, we want to bring out the message that fair performance comparisons of EMO algorithms is very difficult. This is because we need to compare solution sets instead of comparing the solutions, which is very straightforward. Comparing the solution set is not easy. So this is the main reasons of the difficulty of fair performance comparisons in EMO field. And we will cover 4 different factors that can affect the performance comparisons of EMO algorithms. So there are specifications of termination conditions, population size, performance indicators, and the choice of test prompts. And for each of these, I will show examples how these specifications can influence or affect the performance comparisons of EMO algorithms. For the first one, we'll first look into these specifications of termination conditions. For the design of EMO algorithms, we usually focus on 2 aspects. The first is the convergence ability, and also the second one is the diversity ability of the algorithms. So different EMO algorithms, they have different way to maintain the balance between the convergence and diversity abilities. And here we show the 2 extreme examples. One is the convergent-oriented type and the diversity-oriented type algorithms. So for algorithm A here, it is a convergent-oriented algorithms. So it wants to improve the convergence as much as possible. So it will not care about the distribution of the solutions. And for diversity-oriented algorithms, this algorithm B will try to maintain the solution diversity at each generations and slowly move toward the Pareto front. So for these 2 types of algorithms, if we compare these 2 algorithms at this point, which is early terminations, then we will get the conclusion that A is better than B, because A has a better hypervolume than B here. But if we allow the algorithms to have more computational budget and we stop the algorithm much later on, then we may obtain a different conclusions that B is better than A, because at this point, algorithm B has already moved towards the Pareto front and it has a better diversity than algorithm A. So this example shows that the termination conditions can have strong effects on the performance comparison results of EMO algorithms. And there are many different termination conditions have been used in the literatures. Depending on the scenario, the optimization scenario, different number of solution evaluations have been used. For expensive multi-objective optimizations, where we can only evaluate the solutions because the evaluations cost is very expensive, so we can only evaluate a very small number of solutions. Usually the number of the termination condition is very early. And for many objective optimizations, usually the termination conditions can be 100,000. And for large-scale many objective optimizations, we may use 100 million solutions evaluations. And this choice of termination conditions can be reasonable depending on this optimization scenario, but they may not so easy for fair performance comparisons. So this again an example here. So here we have 3 different algorithms, and they are evaluated by the hypervolume values. So the larger the better here. So which is the best algorithm from this figure? So it depends on the termination conditions. if we stop the algorithm here, we will obtain this conclusion that MOED with the weighted sum functions is the best. But if we stop here, then MOED with the PBI function will be the best. So experimental results strongly depends on the termination conditions. And the question here is how to specify the termination conditions for fair comparisons. So a simple suggestion is to use the same termination conditions as in many other papers. This is because it's maybe easy to argue, easy to justify why we use these termination conditions, and it's easy to compare with existing studies. But if we use only a single termination conditions, it only represents a single type of optimization scenario. We do not know how this algorithm perform in different types of budgets. And it may work well on a different budgets, right? So another suggestion is to use various termination conditions and to compare algorithms under an anytime algorithm framework. So instead of using only one termination conditions, we can specify different termination conditions and to check how the algorithm performs. And here, by using the anytime performance comparisons, we may need to reconsider the suitability of the existing algorithm, existing performance indicators for anytime performance comparisons. So here, we show an example here. We use the current populations of the first 50 generations of an EMO algorithm here. And this is the expected results. We expect that the solution set should improve over the time. So here, the ranking, the small ranking means the better solution set. And as we move toward 50 generations, we expect that the ranking getting better and better. But if we use the hypervolume indicators with standard specifications here, for example, 1.1, then we obtain the zero values in the first, in the early generations. So depending on these reference point specifications, we will obtain different type of comparison results here. So for here, this is because the reasons why the hypervolume value is 0 in the early generation is because the solution set is still far away from the Pareto front, and they are not converged yet. That's why the solution set is not dominating the reference point, and that's the reasons why we get the 0 values. But if we use a larger reference point for hypervolume calculations, then we can obtain the expected results, which we can see that the solution set is actually improving over the time. And if we use the IGD indicators for anytime performance comparisons, we may obtain totally different results from our expectations. So these results here show the ranking of the IGD for these real-world problems. So the IGD indicator is not Pareto compliant in the early stage when the solution set is not converged to the Pareto front yet. Yeah, so the IGD, okay, I see questions from the chat box. So IGD value is the full name is inverted generation distance, and it's actually the average distance of each reference point from the sample on the Pareto front to the nearest solutions in the solution set. So the smaller, the better. And usually it can be used to measure the diversity and the convergence of the solution set, but it's not Pareto compliant. So in the early stage, when the solution set is not on the Pareto front, we may obtain different comparison and expected comparison results. And even And because the solution set is not converged yet, and the reference point and the solution set is quite similar to the reference point, then we will obtain a better indicator value for IGD on that solution set. And here we have proposed an idea of the performance indicator for anytime performance analysis. So as we have explained before, when the solution set is still far away from the Pareto front, the solutions are not dominating this reference point. So there's no values here. So one idea is to use a far away reference point, and we can obtain the hypervolume based on this reference point for this population, which is still far away from the Pareto front. And we can use these two reference points simultaneously to obtain a strictly Pareto compliant indicators for anytime performance comparisons. And here we show a result which is based on this idea. And here, if we use the hypervolume with the standard specifications, we cannot differentiate the solution set quality in the early generations. And if we use only the reference point far away from the Pareto front, it may bias toward the boundary, the solutions on the boundary of the Pareto front. So using the two specifications simultaneously, we can obtain a more reliable ranking for this anytime performance analysis. Okay, so now we'll move on to the second difficulties, which is specifications of population size. So if you look at the many studies of EMO, we can see that usually we use the same population size in the experimental settings. And why do we often use the same population size? This is because we want to support fair performance comparisons of the solution set. And the reason is clear if we look at these frequently used performance indicators, for example, the hypervolume and IGD, they can be improved by simply increasing the number of non-dominated solutions in the final populations. So this is an example of calculating the hypervolume indicator. If we have a solution set with only 4 solutions in the final populations, and another algorithm with 8 solutions in the final populations, we cannot directly compare the 2 solution sets because this solution set, we simply increasing this number, the dominated regions here is increased. So it's not fair to directly compare this solution set with this solution set. And the same also for the IGD indicators. But although the use of the stem population size seems to be fair, but is it really fair for all algorithms? Since each EMO algorithms, they can have a different best optimal setting for population size. And here we show an example here. This figure shows the average hypervolume value with respect to the population size for 4 different algorithms. And the population size times the generations will give a constant value. It means that if we increase the population size, then the generation number will become smaller. And if we decrease the population size, then the generation number will be increased. So, and different algorithms, they may need different population size for searching for the optimal solutions. And here, if we use the standard population size for these 4 algorithms, MOED is the worst based on these specifications. But if we if we increase the population size, then MOED with the established functions here is the best. So simply changing the population size, we will obtain a different performance comparison results. So the question is how to specify the population size for fair performance comparisons. So the first suggestion is to use the same population size specification as in many other papers. This is easy and simple suggestions because it's easy to compare with the existing studies and easy to justify your choice because you can say that we follow the other papers. But for fair performance comparisons or to be fair to all the compared EMO algorithms, it may be best to use the best specification for each algorithm and then to select a pre-specified number of solutions from all the examined solutions for performance comparisons. And this idea has been proposed in some studies here. And this slide shows the framework, show the idea of this framework with an unbounded external archive. The idea is for different algorithms, we use the best population size and then to store all the examined solutions in an archive here. And we can use a solution subset selection method to select a specified number of solutions. For example, we can select 210 solutions from these non-dominated solutions, and each algorithm has the same number of solutions, and we can do the performance comparisons in a more fair manner. So here is an example by using a hypervolume-based greedy subset selection algorithms. We choose 210 solutions from all the examined solutions. So this figure shows the final populations, the evaluation based on final populations, as we have already shown in the previous slides. So when we use 210, then MOED is the worst. But if we choose, we select 210 solutions from the unbounded external archive based on this different population size, then we can see that MOED is the best. And also, if we carefully look at compare these two figures here, the 210 solutions selected from these 5,985 solutions, the population size of these 5,985 is very similar or slightly better than the full populations of 5,985 solutions. So this shows that the performance evaluations based on this final population is not necessarily the best for the algorithms. So here, this is the second part. And now we'll move on to the third part, which is for the use of performance indicators. So from this table here, we see that this is the quality indicator used in different studies from 2010 to 2025 here. So many algorithms have been proposed. In each of these studies, we can see that hypervolume and IGD are the most commonly used indicators. Sometimes hypervolume is used alone, and sometimes IGD is used alone, and sometimes they are used together. And hypervolume is the area of volume dominated by the obtained solutions and bounded by a reference point. So we need a reference point to calculate the hypervolume values. The larger, the better for the hypervolume indicators. And for the IGD, it is the average distance from reference point on the Pareto front to the nearest obtained solutions. So this is the Pareto front, and we need a set of reference point to calculate the IGD values. So this reference point, the nearest solution is this one, and for this reference points, the nearest one is this one. And we calculate this average, the smaller is better. Now we will we'll look at these 4 different solution sets. these 4 solution sets has a triangular Pareto front, and they have different distributions. So the question is, which is the best solution set? And by visual inspections, we can easily tell that this one is the best because it covers all the entire Pareto front. And based on hypervolume indicator, we want to ask whether this solution set will still be evaluated as the best. Of course, if we need to specify the reference point if we want to calculate the hypervolumes. So now, if we specify the reference point as 1, 1, 1, which means that the reference point is the nadir point because this solution set is normalized so the range is between 0 and 1. So for hypervolume with the nadir point as the reference point, which is the best? So the answer is this solution set A. And we can see that this evaluation is consistent with our expectations. If we we move this reference point far away to 1.1, then set A is still evaluated as the best by the hypervolume indicators. How about we move more far away from the Pareto front, like R equal to 1.5? Okay, still we obtain this one is the best. And even further, then this is still the best. Even though the hypervolume value is increasing, but the ranking of this algorithm is still the same. So set A is always evaluated as the best by different reference point specifications. So from this example, we think that hypervolume indicators is reliable because set A is always evaluated as the best solution set by hypervolume, independent of the reference point specifications. Now we look at another example. We have these 4 different solution sets. And the difference of these solution sets from the previous one is the shape change from the triangular Pareto front to the inverted triangular Pareto front. And again, we think that set A is the best, right? Because based on the visual inspections, we can say that this is the best. And based on hypervolume with different reference point, what will happen? Now, when R equal to 1, 1, 1 here, which is the nadir point, set B is evaluated as the best solution set. If we slightly move the reference point far away from the nadir point, then set A is the best. How about R equal to 1.5? Then set C is the best. And set D will be evaluated as the best solution set if we use a very far away reference point. So from this example, we can see that different solution sets can be evaluated as the best by hypervolume, simply depending on the reference point specifications. And this is another example for 6 objective problems. So from these problems here, we also have 4 different solution sets. So which is the best solution set based on hypervolume? Here is the answers. So for set A, all the solutions are inside the Pareto front, and R equal to 1, 1, 1 evaluated this set as the best solution set. And set B, set C, set D are evaluated as the best depending on based on different reference point. So set C, which look the best because it has inside solutions and also the boundary solutions, is evaluated as the best by hypervolume when R equal to 1.5. So this example shows that it's not so easy to specify the reference point for hypervolume indicators for fair performance comparisons because the solutions different solution set can be evaluated as the best depending on these reference point specifications. So to understand why this kind of performance ranking is obtained by hypervolume, here we need to see the optimal distributions of solutions for hypervolume maximizations. Here we have two different types of Pareto front. One is the triangular one, and this is the inverted triangular one. So for the triangular Pareto front, which we have seen from the previous example, changing the reference point specifications does not change the ranking of this, the ranking of the evaluations. But if we change the reference point for this inverted triangular Pareto front, we got a different type of totally different performance evaluation results. So the reasons is here. Even if we use a much far away reference point for triangular Pareto front, the optimal distributions for hypervolume maximizations is actually the same, except for this when the null point is used as the reference point, these three corner solutions are not included in the optimal distributions. But for the inverted triangular Pareto front, we can see that different type of optimal distributions are obtained based on different reference point specifications. And to give a more clear understanding on why this kind of optimal distributions is obtained, here we show the example based on a linear Pareto front. So the Pareto front is this linear line, and the reference point when r equal to 1.0, the reference point is here. So when r equal to the nadir point here, the optimal distributions of these 5 solutions, they are all inside. This is because these 2 corner solutions, they have no hypervolume contributions. So they will not be included in these optimal distributions. And if we gradually move this reference point far away from the nadir point, the optimal distributions of the solutions gradually expand towards the two extreme points here. And when r equal to 1.25, we can see that we obtain a uniformly distributed solution which cover the entire Pareto front, and they are evenly distributed. And if we further move the reference point far away from this from the Pareto front, the distribution is not changed. Only the contributions of these 2 extreme solutions, they become larger and larger. So this explains why when the nadir point is used in this, when the nadir point is used as the reference point, these 3 corner solutions are not obtained. Okay. And the question is how to specify the reference point for fair performance comparisons. So the one simple idea is to ensure that each solution in the uniformly distributed solution set has the same hypervolume contributions. So here we can see that this is a solution set with 5 solutions. If we use r equal to the nadir point, then only these 3 solutions have hypervolume contributions, and these 2 corner solutions receive no hypervolume contributions. And for this case, each of these solutions, they receive the equal hypervolume contributions. So based on this idea, we can derive these equations where we can specify the reference point using 1 plus 1 over h. So h here means the interval, the number of interval between the solutions. So here we have 5 solutions, so the h here is 4. And when r equal to 1.25, we obtain a solution set where each of these solutions has equal contributions to the hypervolume values. But this suggestion is useful for linear Pareto front. For nonlinear Pareto front, the use of hypervolume indicator is not so easy. This is because the hypervolume optimal solution set is not always uniform. We see that this is the optimal solution set for hypervolume maximizations. They are not uniformly distributed. So if we have a more uniformly distributed solution set like this, it will receive much lower hypervolume value compared to this kind of solution set. And even for linear triangular Pareto front, uniformly distributed solutions are not always optimal for hypervolume. So here, if we compare these two types of solution sets, this is more uniformly distributed, but it actually receives smaller hypervolume. And these are the better distributions for hypervolume maximizations. So this example shows that the use of hypervolume is not so easy. And we need to carefully specify the reference point for hypervolume hypervolume-based performance evaluations. And we'll look into another performance indicators, the IGD. This IGD is also a very commonly used indicators. And here, based on these 4 solution sets, they are all on the Pareto front, so we don't have to worry about the conversion here, and we don't have to worry about the Pareto compliant here. So based on IGD, which is the best solution set? Since we know that the IGD indicators, they need the reference point set for calculating the IGD values. So the quantity of the IGD, the quantity of the reference point for IGD calculation is very important, and it can bias the performance evaluations of the EMO algorithms. And even if we use uniformly distributed solution set as the reference point set for IGD calculations, the number of the reference point used for creating this solution set can also have effects on the performance evaluations of these EMO algorithms. So here is an example. For this 4 set here, if we use 990 reference point sampled uniformly on the Pareto front, set A, which we think that this should be evaluated as the best set by IGD, is the best only when this number of reference point were used as the reference point. If we use a larger number of reference point for these IGD calculations, then this set B is evaluated as the best. If we increase more number of solutions, then set B is still the best. The same happens to the inverted triangular Pareto front here. This set only evaluated as the best when a smaller reference point is used. If we increase the number of reference point for IGD calculations, this one with no boundary solutions are evaluated as the best solution set. And this is the example for 6 objective cases. The SAM can also observe the set C here with both boundary solutions and also the inside solutions is evaluated as the best when a smaller number of reference point is used. So here we explain the reasons why the solutions with inside solutions are evaluated as the best when the number of reference points increasing. So here, based on these problems with linear Pareto front, we can see that if we use an infinitely large number of uniformly distributed reference point on the Pareto front, this is the best distributions for the IGD minimizations. So here we have 5 solutions, and these 5 solutions are placed in the middle of this segment here. If this solution set is moved slightly toward this part, the IGD value will become larger. So the optimal distributions for IGD minimizations, the solution set with inside solutions will be obtained. Of course, the solution set is uniformly distributed, but the corner solutions is not included in the optimal distributions. So the optimal distributions for IGD are not always intuitive when we use a large number of uniform reference points. So here, if we have a solution set with 20 solutions, this is the optimal distributions for IGD minimizations. And this is on a concave Pareto front. Even if we increase the population size to 50 or 100, we still observe the same patterns here. So there's no boundary solutions in the optimal distributions of IGD minimizations. And this is the case when we have these 10 objective problems. So the situation becomes more severe because we can see that the optimal distributions of this solution set is more inside. In some cases where we cannot obtain the uniformly generated reference point, we use the randomly generated reference point. So in this case, we can see that the optimal distributions is shrink more inside, and the coverage of the optimal distribution, it cannot cover the entire Pareto front. Okay, now we'll move on to the last part of these presentations, which is related to the choice of test problems. So the choice of test problems also can influence the evaluation results. So this is example here. We show the best algorithm percentage for each test problems for 3 to 10 objective based on different type of test problems here. So if we focus on DTLG problems, if we use only DTLG in our experiments, we will obtain the results that NSGA2 is outperformed by many objective algorithms for this class of problems. And if we change the test problem we use in the experiments, we will obtain a totally different evaluation results. So now, if we use this test problem set, we will obtain the conclusion that NSGA2 outperforms many objective algorithms on many objective minus DTLG problems. So by simply changing the test problems here, we'll obtain totally different results. And this change here for DTLG 1 to 4 and minus DTLG 1 to 4, the difference of these two problems is simply minimizations of the problems and also minimizations with a negative sign here. So this minus DTLG problems is actually the maximizations of the DTLG problems. But changing this by using a negative sign in these objective functions here, we obtain a totally different Pareto front shape. Then we obtain a totally different performance comparison results. And it's important to use real-world problems for performance evaluations. So these problems, they are actually good for, the artificial problems is good for us to understanding the behavior of algorithms, but we also need to test our algorithms on real-world problems. And recently we have seen that there are many different types of real-world problems that have been proposed, which are the collections of different engineering problems or real-world problems from different application fields. And one clear difference of the Pareto front from this real-world problem set are that they have irregular Pareto fronts from which is different from this type of regular Pareto front. And here show the comparison results on the artificial test problems and real-world problems. We can obtain totally different comparison results of these 10 EMO algorithms between the DTLG problems and the real-world problems. So this figure here shows the ranking. The smaller the number, the better the ranking here. And here are more experimental results here. And we can observe that for these minus WFG problems, it has more similarity to the performance evaluation results on the real-world problem sets here. So again, this emphasizes that we need to use more realistic test problems so that we can understand how, so that the algorithms are not overfitting to artificial problems. For constraint multi-objective optimization problems, we also observe similar patterns. If we use only artificial constraint multi-objective optimization problems, we see that the state-of-the-art algorithms perform much better than the NSGA2 with the simple CDP constraint handling technique. But if we use a real-world CMOPs here, we obtain a totally different comparison results. NSGA2 is evaluated is the best among the other algorithms. So here we explain why this kind of ranking is obtained. Here is one of the example of artificial CMOPs. The characteristic here is that this kind of test problems, they have large infeasible regions here. So this is the feasible regions and this is the infeasible regions. So for NSGA2, it's not easy for the solutions to cross over these infeasible regions because the NSGA2 is a feasibility-driven, feasibility-first algorithms. So when it arrives here, it cannot move to this part here. But for the more recently proposed algorithm with more complicated mechanisms, for example, we have this pull and push search. So the algorithms can first ignore all the constraint conditions and quickly move to the unconstrained part, and then go back to the constraint Pareto front. So usually, recently proposed algorithms, they can perform very well on the artificial CMOPs. But for constraint multi-objective optimization problems for the real-world CMOPs, we can see that the infeasible regions and feasible regions of the problems is different from the artificial one, where this artificial one, they usually have large infeasible regions between the Pareto front. But here we can see that, for example, we see that different type of feasible regions can be are present in the real-world CMOPs. And this is in the objective space. So this is the feasible regions and this is the infeasible regions. Sometimes we can observe that there's actually no clearly disconnected feasible and infeasible regions in the real-world CMOPs. And this is in the infeasible regions and feasible regions in the decision space. So we can see that the shape of the constraint Pareto set Pareto set is more simple in real-world CMOPs. So basically, the message of this talk is to explain why different performance comparisons can be obtained by different factors. And for this choice of test problems, the suggestion is to focus on a class of problems and not the suggestions is to focus on a class of problems and to demonstrate that the usefulness of the proposed algorithm on that class of the problems. And we also suggest that we can design a more general, robust, and flexible framework which can be easily modified for different problems and to demonstrate its usefulness on various problems. And the goal of performance comparison is not to find the winner of the algorithms, but we want to understand why different types of results is obtained, and we can explain the results that we obtained for the results that we obtained. And finally here, this is the last part of our presentations. So we will also have a tutorial in WCCI here on this topic, and we welcome you to join our talk if you are interested in this topic, and we can discuss more details in person for improving or to design more fair performance comparisons for EMO algorithms. And also, last but not least, we will have a more specialized EMO algorithms in EXTER in April next year, and the paper submission deadline is this September, and we welcome you to submit your work to this conference. And that's all for my presentation, and thank you very much.
Thank you so much for your very interesting talk. I think this webinar you discussed the 4 very important but quite interesting difficulties in EMO. I believe those are very important for the students or researchers who are working on EMO. I think now let's move to the question part.
Okay, now
I think the first question, what is IGD, you already answered, right?
Yeah. Yeah, and then the next
Yeah.
question is why not we use an archive to store all non-dominated solutions and compare the archive obtained by different algorithms regardless of the population size. Okay, so I think the question is to directly compare all the non-dominated solutions. So different archive can, since the archive is unbounded, so different archive obtained by different algorithms can be different size. And why we do not directly compare them? I think this is the question. So yeah, any suggestion to set the number of points? Okay, so the first question, why not we use, yeah, thank you for these questions. And yeah, this can be a good idea, but it can also be expensive to calculate all to compare all the non-dominated solutions in the performance evaluations, because for example, if we calculate the hypervolume indicators, if we have 1 million of solutions in the archive, the millions of non-dominated solutions in the archive, it may be very difficult to calculate it. So it may be better to select a pre-specified number of solutions for comparison. Yeah, so this is my answers. Yeah. And then the second question is any suggestions to set the number of points in the reference set for IGD for a given problem? This is another good question. Yeah. Actually, currently I do not have any good answer for these questions. Yeah, so maybe we can discuss it later. Yeah, and then for another question is everyone, I want to know, this is an article. Here's what the title, thank you. This is an article, what's the title?
So is any publications related to your
Oh,
talk?
yeah. Yeah, this talk is mainly from the one IEEE CIM magazine papers, which the title is Fair Performance Comparisons of Evolution Multi-Objective Optimizations. And I think it also shown in this slide here. Maybe I can show. This one. So difficulties in fair performance comparisons of multi-objective evolution algorithms. And then the next question is, can you please explain the real-world example where these algorithms are applied in the real world? Where these algorithms, I see. So these questions probably I cannot answer right now.
Okay, probably move to the next one, I think.
Yeah, the next one. Yeah. So probably you can send me an email and we can discuss through the email for that questions. Can you please explain the real world example where this algorithm applied the real world? Yeah. And the next one on the slide where you show that NHA2 was first outperformed. Then NHA2 outperformed others. Was it IGD best comparisons? Oh, that is IGD best comparisons. Yeah, but even if we use hypervolume based comparisons, we also obtain similar results. And thank you for your detailed study. How can we use your extensive study to fix reference point for hypervolume matrix for an arbitrary problems for which the exact Pareto front is not known? Oh, thank you for these questions. It's a very good questions. Yeah, in this case, when we do not know the exact Pareto front, usually usually we will obtain the approximated Pareto front based on the non-dominated solutions found along the evolution process, and then we can do the normalizations and use the suggested values 1 + 1 over h. That is one suggestions, but the important point is we may need to normalize the Pareto front. And we get the PPT. Yeah, we will.
Yeah, I already shared the link in the chat, and we will post all the video and slides in the link.
Thank you. And the last question, I think, is I have questions about random seeds in EMO performance evaluations. For hypervolume and IGD, is it more appropriate to compute the indicators separately for each independent run, and then report the mean and standard deviations across seeds rather than merging solution sets from all seeds before computing the indicator? Is it more appropriate? And would merging all seeds overestimate the performance by evaluating an accumulated archive instead of typical single run? Yeah, usually we will compute the indicator separately for each independent run, and then report the means and standard deviations across seeds. So we don't usually merging solution set from all seeds before computing the indicators. Yeah, I think your way is what we usually do. And would merging all seeds overestimate the performance by evaluating and accumulated? Yeah, I think yes, because if you merging all sets, it means you're merging all the solution sets. You combine all the solutions into one single solution set and then do the performance evaluations. In this case, the number of solutions is much larger than the one that obtained by a single round. So this, for sure, it will overestimate the performance, I think. So is there a way to choose an optimal reference point in hypervolume calculations? Yeah. And yeah, thank you for these questions. Actually, I don't have an answer for these questions. It's not so easy to say which reference point is optimal for hypervolume calculation. It actually depends on the problems and the Pareto friendships. And I think we still need to work along this direction so that we will be able to have a better suggestions on the optimal reference point in hypervolume calculations. Yeah.
Thank you.
Thank you very much for all the questions.
Yeah, thank you for all the questions. And it seems that we don't have more questions now. And thank you again for your great talk. I think it's also for me is my first time to listen your this talk, and I learned something about emo from here. Thank you so much. And also thanks all the participants for the questions and attentions. Thank you. And also thanks Tom and Neil and Joanna here. I think now probably we can stop here and you can have a rest after.
Thank you very
Thank
much.
you.
And thank you.
Thank you.
Yeah, thank you everybody who joined this seminar webinar and also all the questions. Thank you very much. Yeah.
Thank you. And all the videos and slides will be available on the IEEE CIS, the link shared in the chat. Thank you.
Thank you.
Okay.